while my device is working, I'm going to go ahead and finish up chapter 20. I think I'll let you all weigh in if you like, but to me, this is one of the easiest chapters that we'll do all year, and to enhance some of your grades, if you'd like, I can do an individual chapter test on just this one chapter, or we can combine it with another chapter after spring break. So please message me your choice after you've had a chance to do some of the homework and quiz problems. So nuclear fusion, the opposite of fission. Fission is taking large atoms and nuclei and breaking them apart. Fusion is taking very small nuclei, like a helium nucleus or a hydrogen nucleus, and taking two of them and slamming them together and creating something larger. Okay, think taking two little mini marshmallows and slamming them together as hard as you can and making a big marshmallow, okay, as opposed to taking a large, ginormous marshmallow and splitting it in two and sharing it with your friend. That's the difference between them. So nuclear fusion, combining two small into larger. Two light nuclei form a more stable nucleus. This is very important because this is exactly the kind of reactions that happen on our sun. Okay, that's where a lot of research is focused right now, because if we could ever harness that energy, oh my goodness, think about how much energy we get from the sun. If we could ever harness even a small amount of that, we would end all of our energy problems. They would be gone. So you all need to get to work on that, and I'm not even kidding. Here's a couple of examples. I'm not going to even try to go into balancing these with you because I feel like I've balanced 50 of these for you. I do want to draw your attention to this one problem right here. With this, here you have helium, but it's got an extra, one less neutron. And if you have two of those, it came from the product of this reaction here where you have a deuterium and a hydrogen slamming together, and it makes this helium nucleus that's missing one neutron. You get two of those together and slam them into each other. Now you have a nice hydrogen, and look what you have, two protons. See this two right here? When you're balancing these, you have to take that as you have one hydrogen plus another one hydrogen. Take them separate, or that means you have two of them together. Okay? And that's exactly what they've done in this bottom one down here. Now you take each of those two right here and put them here. Okay? And that's what you get. So there's your balance equation. All right. So there you go. All right, and then we have nuclear fusion. Again, this is just talking about the temperatures that this has to take place at, because they only happen at very high temperatures. Think how hot our sun is. It's literally 1,000,000 degrees, so it's very, very high temperatures, and that's a very huge concern. But the amount of energy that can be released in this is very, very large indeed. So here's some of the advantages we've been talking about. Fission, let's look at the advantages of nuclear fusion. Very cheap and almost inexhaustible. Think about the sun. Okay, the amount of hydrogen that's on the sun. The energy that we get from the sun is this kind of energy, thermonuclear. Our sun is nothing but a ginormous thermonuclear reactor that fusions together hydrogen and helium atoms through exactly this kind of process right here. exactly this kind of process right here. These are the reactions that happen on the sun all the time. And all of our heavy elements that we have on Earth came from these kind of reactions from the sun. So also, the process, you don't have the nuclear waste that we have with fission products. So there's not going to be any kind of meltdowns. You're not going to have to worry about that. So you got those super extreme temperatures, and things don't work well at extreme temperatures, so you got a lot of technical difficulties there. Got to find a container that can withstand those kind of temperatures. You got to find equipment that can withstand those kind of temperatures. So those are all problems that you got to deal with. So if we could make thermonuclear or nuclear reactions, fusion reactions happen at a lower temperature, oh my goodness, at the money you would make. So here's one thing that's in the works right now. Is they're talking about trying to get some sort of magnetic field to generate and confining it, the nuclear reaction within that magnetic field. And they're doing it by making this donut shape. So seeing some of these shapes and hearing some of these terms should make some of the sci-fi movies, Iron Man and some of these kind of things, make sense and see where they're coming from. They're not just made up. So, here's another example, the hydrogen bomb, the thermonuclear bomb. These are just some examples of things that we use nuclear fusion for. And here's the reaction. Okay, you got some lithium and then hydrogen fused together, and you get 2 alpha particles. And there's huge amounts of energy being given off. Again, here's the balanced equation. I don't see a need to go through this again and again and again. Okay, and then let's talk about what we use these for. One of the most important things is medicine, and I did go through some medical testing myself, and I'm sure you know people that have as well. But we use them for so much important things these days in medicine. So we get, we use isotopes in radioactive testing and to treat cancers and things like that. So here's one thing, thiosulfate, when it's treated with dilute acid, you get this right here, okay? And so then you get this structure, and I'm going someplace with that. We come up with radioactive tracers. Right there you go. And so if you have these radioactive isotopes that don't leave any residue behind, we can use them in our bodies and trace them medically. Think about people that you know that have had to have medical testing and they've had to drink that chalky white stuff. Well, they were actually drinking radioactive tracers, and then they can have testing to actually see where does that radioactive isotope go throughout their body. And they can find blockages, they can find all different kinds of things. So they're used so much for medical diagnoses. Sodium-24 is used for obstructions. This is the stuff you're drinking when you're drinking the chalky stuff. Iodine-131 for thyroids for years and years and years. Iodine-123 for brain images. I had to have that after a car accident many years ago. Technetium is used, used in cardiac patients all the time get technetium. So these are important things, and here's some of the other radioactive isotopes that are used. And there's some, here's your technetium, that 9943 technetium, that M just means that it's metastable, okay? All right. Or is it that it's in its excited state? And this is how they can use that excitable isotope of technetium. So there's that gamma symbol right there. So they can look at your liver, they can look at your heart, they can look at your lungs, and they can find these tracers using simple Geiger counters and find where those are. And with those tracers, they can find problems and diagnose. And then we're not going to talk too much about this, but because we already know too that the biological effects of radiation can be also bad. We can have adverse effects too. And a RAD is short for a radiation absorbed dose. How much radiation do we absorb? And you know, if you absorb too much radiation or get too many RADs, that's not good. And we can get them by background and by going to the dentist, but the vast majority of it comes just from background radiation, from radon and other things that are in our environment. So, cosmic rays, just by our body, by getting medical and dental x-rays, by traveling. Fallout from weapons tests. Now, we're not going to be subject to that too much anymore, but if you're living near Chernobyl, where Chernobyl was, and back in the day when there was so much nuclear testing going on, where they were doing all that, that was a big deal. And then from nuclear waste, you get a little bit from that too, unless you're living close to the site, and then it's much higher, of course. So if you've got free radicals, these are molecules that have unshared pairs of electrons. Now, we drew molecular symbols, and we drew their electrons around there, and you saw the unshared electrons. If you have those are free for the taking. You know, if you have something that wants to join with those two electrons, or that's attracted to those two electrons, those can be called free radicals. If they're not paired with something, then something can be attracted to those or even snatch them away. They're called free radicals, and they're very, very reactive, or they can be very, very, very reactive if they are not combined in a compound. And if they're in a compound, then they're not free radicals. But if they're not, then they can be called free radicals. And in tissues, these free radicals can attack cell membranes. Now, free radicals, that's a big buzzword in advertising right now, and wrinkles and all those kinds of things in makeups and foundations and beauty industry. So it sounds like a bad thing, but they can also be used for good. All right, so there you go.